Welcome everybody to the April 25th edition of Fire on the Fives, brought to you by the National Weather Service. This seminar or webinar is a fire environment webinar where experts in the field are able to bring presentations and information out to the field and share it with other fire environment practitioners, and ability to share the information amongst each other. Let's go through some logistical information first before we start our presentation. Please ensure that you mute your phone or that you use the audio pin provided. If you would like to ask questions later, you need to enter the audio pin that you were given when registering for the webinar. That way we can unmute you when you have questions and you are able to ask. If you did not enter that pin, you will not be able to get off of mute. If you have questions during the presentation, please use the question box in the dashboard of the GoToWebinar software, and we will acknowledge that you have asked a question and we will unmute you to ask that question. These talks will be recorded and posted to the National Weather Service YouTube. If you do a search for NWS Fire Fives, you will see a Fire on the Fives with all sorts of different Fire on the Fives that have been recorded from past presentations, and this one will be added as soon as we can after the conclusion of today's seminar. So again, welcome to the April 25th, 2018 edition of Fire on the Fives. Today we are pleased to have Dr. Mark Finney. He is a research forester with the U.S. Forest Service, in the Missoula Fire Sciences Laboratory, which is part of the Rocky Mountain Research Station. And today, Mark will be talking to us about fire spread models. With that, I am turning it over to Mark, and take it away.
Okay, so I hit show my screen, right? Yep, there we go.
Correct.
Okay, good afternoon, everybody. So I am going to use a presentation that I gave about a half a year ago, and concerning a lot of the research that we're doing here at the Missoula laboratory. And it's focused on some of the fine-scale physical processes that go on in fire spread, because it's kind of hard to believe here, but in the year 2018, we actually don't know how fire spreads. And that's something that has arisen because we've here and elsewhere in the world have been focused on providing models and tools and other practical kinds of decision support systems, rather than really delving into the unknowns about how fire spreads and these physical processes. So I'll show you what we've been finding. There's some really interesting stuff here that hasn't been known before until very recently. So our goals here in doing this very basic research is to, first of all, provide better training and education for our firefighters, and I guess that would go to National Weather Service people too. Provide explanations to correspond with what people's observations are. And so a lot of our fire people are out on the fire line. They don't have time to model anything. What they really need to do is be able to interpret what they see and understand what that means. So training and education is probably our first priority. The second is planning and mitigation. Most of the tools that we have in use now for fire prediction are actually used in planning efforts, because you don't have to have a fire in order to run these models. And so understanding how to do fuel treatments and how to understand fire risks to communities, that all involves planning type applications of models. And it outnumbers the operational uses on active incidents by probably 1 in a million for just operational stuff. So so the third priority here is actual prediction on active incidents. Fire models are used a lot on that, but really we're only talking about a few thousand incidents a year where there's time and an organization to actually implement those models in a operational setting. So like I said, the demand here is a lot less than for training and mitigation. So we also use models for ecological modeling. We need reliable models to incorporate in a lot of these global climate change models and things like that that reflect fire as an ecosystem process. The other thing we do here in the lab, and you'll see how important it is throughout the talk, though, is what I call scaling. We have a laboratory where we do a lot of indoor fires, and what we need to make sure is that the experiments we do at the fine scale actually scale up to the field scale, where the wildland fire questions actually become important. So it doesn't really matter whether we do a good job understanding things at a laboratory scale if those things don't translate to the field scale. So let's see. Most of the, as I said a little bit earlier, most of the effort that's gone into wildland fire modeling has been concerned with how fast fires spread. It's not really too much of an overstatement to say that we've been preoccupied with fire spread rate as a primary target of predictions, but there's lots of other behaviors about fires. So when we focus on fire spread rate, which is important, of course, it indicates how fast they're moving and how fast they're growing in 2 dimensions. We are interested in the effect of wind, the effect of slope, the effect of the fire on how fire spreads. But in order to really answer this question, rather than jumping straight to how fast fires spread, we need to understand how they spread. So how do fires spread? And when can they spread? Those things have never been addressed. And that's, if we don't know the physics of how they spread, it's very, very difficult to get down to that lower left box there of how fast they spread. So one thing we realize in wildland fire is that fire spread is a strongly coupled system. That is, you see this little diagram right in the middle where we have combustion energy release, heat transfer, and ignition, and that's all in a circle of life, just like the Lion King, a circle of life where there's no independence of any of them. And so this makes it hard to study because you don't actually have a place where you start and it goes through a linear kind of progression to where you get to fire spread. The whole fire spread is a circle. It's a strongly coupled system. And so what we try to do is to take apart these pieces, combustion and energy release, heat transfer and ignition, study them separately, but we always have to fit them back together again to understand the system, the entire system. So some of the questions we address on ignition are, how do fuel particles ignite? And there's some very surprising things here. And we have to always keep in mind we're not just dealing with dead fuels, but we're dealing with live fuels as well. And this makes it particularly different from, say, structure fire engineering, fire protection engineering, where they pretty much have man-made in composite materials rather than live vegetation as a principal fuel. We need to know how long fires burn, the burning rates, what's the rate of energy release, right? And for live and dead fuels, that's extremely important because if we don't know the source term, we don't know the energy release rates, we can't really do the rest of it. And then heat transfer. We're principally talking here about roles of radiation and convection, and I'll make a strong point of why these are the main ones at this point. But believe it or not, we haven't done a good job in the physical fire research of explaining the roles of each one of these or the limitations of them. So these are just the pieces that we're going to go through a little bit today. And finally, when you address all of those, you understand all of those, you need to piece it back together to understand how fast fire spread. And that was our original question. So let's just examine here what we found with a couple of these linkages in this circle. That is the roles of radiation and convection in producing ignition, in this case, dead fuel. So to state the obvious here, wildland fuel is totally different than, say, industrial fire problems and in building fires. We're primarily dealing with fine fuels, that is less than 1 millimeter in size. These are pine needles and grasses and leaves and small twigs of shrubs and trees. They're discrete particles, and by being discrete, they're separated by air. And this is very important to the heat transfer and the ignition processes that are relevant and quite unique to wildlands compared to industrial fire environments and live vegetation, of course. Let's see how unique this is. We have a radiant heater. This radiant heater is putting out 37 kilowatts per square meter. And just for, I'll replay the video. And what we're doing is we're subjecting two different particles to this radiant heat. And so the particle on the left is a thick particle. It's 12 millimeters in diameter, around a half an inch, and the one on the right-hand side is 1 millimeter particle. And so we expose these to 37 kilowatts per square meter, which is quite a bit. The solar constant is about 1 kilowatt per square meter at the top of the Earth's surface. So, and you notice here that the fine particle is just sitting there. And after about 30-odd seconds, you can pilot ignite the gases coming off of the 12 millimeter particle. And yet the 1 millimeter particle, the thin particle, the size of a pine needle, is not even smoking. It's not decomposing. And when you present this kind of a video to even a lot of well-established fire scientists, it takes them quite a while before they figure out what's going on, because most of us would think that a 1 millimeter particle would be easier to ignite than a 12 millimeter particle, right? It's just how we would light a campfire or something else. But what we're witnessing here is the fact that the 1 millimeter particle is cooling off in all the cold air that's surrounding it so efficiently that it's not heating up, whereas the 12 millimeter particle, having a very thick boundary layer on it, is not able to cool off by convection. So if you put a thermocouple on these particles, this is the kind of graph you would see. Over time, on the x-axis, the temperature, on the y-axis, the temperature starts to rise for both particles, but the 1 millimeter particle in blue achieves a temperature that's less than 200 degrees Celsius and stays there, just kind of bounces around because it's losing all of that heating that is arriving by radiation. It's losing it through convection into the cold environment. And so this is not forced convection. There's no air being forced past the particle. In other experiments that we've done, the forced convection, of course, can be demonstrated to be 3 or 4 times more effective at removing heat than just free convection or natural convection. So in most fire environments, you have wind, not just ambient wind, but fire-induced flow near the fire as the fire front approaches. And so there's always a lot of flow past these fine particles. The thick particle, the 12 millimeter particle, rises up to a temperature where its surface can sustain a flaming ignition, and then it gets hotter from there. Okay, and so here is a similar experiment. Here we have a nest of excelsior, very dissected and open and fluffy on the right-hand side, compressed, the same material compressed on the left-hand side. And look what happens. I'll replay that again. Try to replay it. Yeah. And so here we have the same material, just the compressed version of it is able to start pyrolyzing, decomposing thermally with that heat, and it auto-ignites. It doesn't even need a pilot on the left, and that's in about 20-odd seconds. The same exact material can sit there for hours and hours or days and never even char, simply because it's got enough access to cold air around the particles to cool it off. So if you find that surprising, you're in good company, because many fire scientists around the world haven't bothered with even such simple demonstrations to try to understand the roles of radiation and convection. And so what we learn from something simple like this, and it's been researched in much more detail, which you can read about if you'd like. But what we learned from this is that radiant heat transfer that is so important to causing physical injury to human beings, or even to large surfaces like walls of a house, is largely irrelevant to the ignition processes in wildland fire. So even though you're standing next to a fire that is putting out, say, 37 kilowatts per square meter, or 100 in a crown fire, that radiant energy is not very important to the spread of that fire in the fine fuels. It is not that important to ignite, raising them to ignition temperature and to spreading the fire. That is a big surprise. And so this just explains a little bit graphically what I've just said, is that the radiant heat. Yes.
Mark, this is Larry. I have a question on that previous slide. Did you guys happen to test, or did it make a difference on slope, or do you think, regardless of what the slope is, just the fact that it's compressed or dissected or larger or smaller at that scale wouldn't make a difference what the slope was?
Right. It doesn't make a difference. It's all about the incident radiant flux on the particles and whether or not they are surrounded by cold air that can be replenished.
Okay. Thank you.
Yes. That's okay to interrupt me and ask questions. I don't mind. So this slide just basically explains that the radiant heating absorbed by the surface, it is absorbed by the surface. It's not that the particle isn't heating by radiation. It certainly is. It's just that the natural and forced convection of the cold air past it is taking that heat away as fast as it comes in. And this is happening because very fine particles have a very thin boundary layer that's easily disturbed by airflow across it. A long particle, long surface, has a thicker boundary layer that is harder to disturb, and so it's kind of insulated from contact with the cold air. And so this is the reason why you have cooling fins. I've got a couple of little stock illustrations. There are cooling fins on your CPU and on your engine. It facilitates convective heat transfer with the cold air, and that's how your engine or your CPU stays cool. So our wildland vegetation basically has the ability to stay cool when subjected to very, very high radiant fluxes. All right, so next comes the next question regarding regarding heat transfer and ignition, is that if it isn't radiation, then pretty much you have to have convection. Right? Conduction occurs between or within a solid, and since we have these fine particles are separated by air, conduction between them is not possible. So it has to be convection, and that means flame contact. In this case, convective heating. I talked about convection before as convective cooling, but in this case, I'm talking about convective heating. So the two questions that have never been asked, and certainly not answered before, is how does that happen? What keeps hot flames down in contact with the fuel? If they're hot, they want to rise. And how would they stay down in the fuel? Because if they don't stay down in the fuel, then they can't contact the fuel. Right? So, and then the second question is, what is the mechanism of forward convective heating? And I have these illustrations down below, these little sketches that have been included in many different papers. And it's impossible to see from most of these how you would get the flames to stay down in the fuel and how they would produce forward convective heating. So I'm going to show you what experiments we did to understand that. So everybody knows that flames are hot, and by being hot, that means the gases in the flames are low density. And at sea level, the gases in a typical candle flame or any wildland fire flame, it's a diffusion flame, or the temperature is all about 1,000 degrees Celsius, plus or minus. So the density of the gases is very low. It's about a quarter of the density of air at sea level. And so that means it's very, very buoyant. It wants to rise. It's even more buoyant than a helium balloon. And so that's why we get a candle flame that is oriented vertically on Earth, is because those hot gases, they rise when gravity pulls down on the cold air, and which forces it up. But if you take a candle and you put it up on the space station, even if you have plenty of oxygen and fuel, everything for combustion, you don't get the same kind of candle flame because there's no gravity to allow buoyancy to remove all those hot combustion products. And so gravity is the key. Basically, if you didn't have gravity, you wouldn't have forest fires. So I think someday, if we're able to invent an anti-gravity machine, you would see very, very effective fire suppression. So buoyancy is very key, and it all has to do with the density of the air inside the flames or the gases. We see that buoyancy manifests itself in different kinds of flame behaviors. One is kind of a steady candle flame going up, but you've all seen candles flicker. in the past, sit there on the table and they flicker. Well, at a much larger scale, you can see what's called pool fire puffing, and that's what this video is here. This is a 1 meter diameter pan filled with ethanol, or maybe it's isopropyl. It could be ethanol. Doesn't matter. You can burn anything in there. Let me go back and replay this. And if you burn a circular pool or even a square pool of liquid fuels, could be solid fuels too, it will produce this very periodic kind of puffing behavior. And the puffing is caused by buoyancy. It's not caused by combustion. It's a buoyant instability. What happens is the hot parcel has to try to rise. Let's try to. The hot parcel tries to rise. It originates at the rim. It works its way towards the middle of it. As the hot parcel rises, that volume of air has to be replaced by something else. It has to be replaced by air coming in from the side or coming from the top, and so it causes a circulation there. And until that puff is out of hot air, of hot gases, is out of the way, you can't get the formation of another puff. And so that's why the puffing tends to assume a very periodic behavior here. And it's another way to think about this is, it's probably not news to you, but if you take a basketball and you push it down below the water in the surface of the water in a swimming pool, and you let it go, it's going to rise up and float to the top. But by doing that, it's not going to leave a hole in the pool water, right? It's going to be filled in by the water rushing back in to fill that void. And the same thing with gases evolving during open combustion. The gases are going to rise, and it's got to be replaced by something else. So how it gets replaced is what forces this periodic puffing behavior. This is a graph from one of many different studies in engineering literature where people have examined pool fires, and they found that the only factor that matters in the puffing frequency of a pool fire is the diameter of the pan. And you can see that this goes from all the way from tiny little 1 centimeter pans all the way up to 100 meter. So across a wide variety of length scales, you get the frequency dependent only on the square root of the diameter of the pan. And all those symbols on there are different fuels. So you can see that the fuel doesn't make much difference. And they could put, you could put pine needles in there, you could put wood, you could put pretty much anything, and it would puff about at the same frequency. And the reason for this, it's really important for scaling, is that the temperature of the combustion, of the flaming combustion, is all about the same, irrespective of what fuel you're burning, as long as it's a hydrocarbon fire. As long as it's not unconfined combustion, the temperature is related to the amount of oxygen that diffuses into the fuel-rich core of the coming off the pool. And so the temperature is always about 1,000 degrees, irrespective of what fuel you're burning. So that means that the biggest fires and the smallest fires all have about the same temperature, same density, and therefore the puffing scales. This is super important. So if you look at this is the salt fire in Montana, or maybe it's Idaho border there, from a couple of years ago. You can see the series of billows in the plume, and you'll see this kind of large scale puffing. That's a forest right there. That's not grass. And I'll play this video again when it's done, but that regular billowing of the plume is related to the puffing frequency of the fire, and the periodicity is related to the size of this fire. So it's possible to back calculate, out knowing the periodicity, calculate the diameter of this fire. And let me try to replay this. Oops. There you go. So you can see the very regular billows there, and that is an example of very large scale puffing in a forest fire. So the buoyant dynamics are going on. They're at work in our large scale wildfires as the same as they are in our laboratory fires, and it's due to buoyancy, to density. So remember, I said it's really important that we get scaling, that we study phenomena that can scale study in a way that we understand the scaling all the way up to the field scale. So another manifestation of these buoyant instabilities can be seen in the geometry of spreading line fires. Most of the time when we think about a wildland fire spreading, we kind of think about it as a line of flaming combustion, where it's advancing across the fuel complex and spreading as a line, burning out behind and spreading as a line. It doesn't have to be that way, but and there are certainly other geometries like mass fires, in other words, area burning. But let's just talk about a line fire. If you look at these pictures, your grass fire, a bunch of grass fires actually. The one thing you notice is the very regular peak and trough pattern of those flames, right? Look at the separation between those flames. It's extremely regular. And I picked pictures out that are really good examples of that, just so you can see it. So hopefully everybody sees that the flame zone, the flame front, is defined by a bunch of peaks, flame peaks, and then there's a gap in between them, and then there's another peak. And there's kind of a very regular pattern across there. And we see that not just in spreading fires, but we see that in stationary fires as well. This is a 52-foot long crib fire. It's basically sticks that are stacked together. We do this, these kinds of experiments, not just big ones like this, but little ones too, to understand burning rates. And I'll show you an example at the very end here about some experiments in burning rates. But we did a very long crib fire here, basically see if we could look at the scaling of these flame peaks and troughs and those dynamics for a big stationary fire. This was done right out in the back of the fire lab here one winter. And those flames are about 6 meters, about 20 feet long, sticking off of there. Okay, we see it in crown fires. So this is a picture of the Northwest Territory burns in the late 90s, and you see a very regular pattern of peaks, traversing laterally across the flame front. So this isn't just a small scale issue. It occurs in grass fires and crown fires and stationary burns. It occurs apparently everywhere. Well, we studied this thing. I mean, first of all, we didn't understand that that was even meaningful until we began to study this. But we were trying to answer the questions: how do flames stay down in the fuel, and how do they propel the fire forward? And so the way we do this in the laboratory is with very artificial fuels. It's important to control for the variation and the characteristics of the fire. So the technique we came up with is to use cardboard. And so these are examples of cardboard being lined up in our wind tunnel in different densities and different heights, different thicknesses of the material. And this is on a slope. We have a big sloping table that we can examine slope effects on fire spread. And the fuel here is cardboard. It's just like the same exact cardboard on the back of a pad of paper. In fact, we buy it from companies that make that stuff. And we put it through our laser cutter. We design the fuel particles on the computer, and then we just print them out. So we can create any kind of fuel particles. We want thick ones, big ones. I'll go back. Thick ones, little ones, short ones, fat ones on this, and pretty much engineer whatever kind of fuel bed and then fire behavior that we want to. So that's how we study in the laboratory. In the past, burns have been conducted in this lab now since 1960s, but they were always using natural fuels or Excelsior, and then pine needles. But the problem with that is you can never really control the particle properties, the placement, the density, all those things. And so you have heterogeneous fuel material at fine scales, and you can fail to see important flame structures that are there. They're just obscured by all the variability in the fuel. So let me show you this fire is coming head on at us in a wind tunnel. Let me show you what's going on here. This is what we see. Once again, you see peaks and troughs, right? There's three principal peaks, although now and then it breaks into four. Three principal peaks. In between, I'll play this video again. In between those peaks, you're seeing just clear air, and you're seeing the flames sitting right down into the fuel bed right there. All right. So I'm gonna replay this video. So watch carefully here. The peaks are places where the flame is going up, and the trough is where the flame is going down. And so this is very similar to the puffing pool fire example, where the puff rises and is replaced by cold air coming down. And so if we look at what's going on here, is that we end up with updrafts. There are zones of convergence. That's what the peaks are. And then given there's a circulation there, there's a downdraft in between the peaks that is forcing the flame down into the fuel. Right? And it's kind of counterintuitive, I think, that because these flames are hot, they're buoyant, they want to rise in the presence of gravity, that there has to be an equally strong downdraft to the updraft. So the flames are going up, but in order for them to go up, something has to come down to replace it. And it's where it's coming down that it's actually forcing the flames down into the fuel in contact with the fuel. Where the flames are going up in the air, that's largely irrelevant to heat transfer in these fires. So when the flames are sticking out of the fuel, no matter how tall or spectacular they are, that's not where all the action is. That's not where the heat transfer is taking place to spread the fire. It's in the troughs, it's in between, where the cold air is forcing the flames flat down into the fuel. So I have another video here, I'm pretty sure. Yeah, so this is looking down on the fire. It's a different fire, but you're looking down on the fire, and what you see is the fire spreading from the bottom to the top. What you see is all these little concave parcels, these little dish-shaped regions within the flame zone, and then they move through the flame zone. We're not entirely sure what these are, but they're reminiscent of what are called Rayleigh-Benard cells, and Rayleigh-Benard cells are seen all over the place at many different scales, from the oil in your frying pan all the way up to the atmospheric scales. You can see them a lot in the satellite images, like the GOES-16 satellite images of the open and closed cells in the cloud, formed by clouds. And in gases, Rayleigh-Benard cells tend to go down in the middle. In liquids, they tend to go up in the middle. It's a reverse circulation. So what we think we're seeing here with this is Rayleigh-Benard cells as a manifestation of this thermal instability, and they have their own little donut in circulation pattern where it's forced down in the middle and up at the edges. Okay, and those little parcels move through the flame zone and splash forward as they exit. And so this next graphic, this next video is a flow tracking analysis of some of the video. And watch down in the trough there, you'll see it says forward bursting in the troughs. And as these Rayleigh-Benard cells kind of pass through the flame zone, they kind of burst out forward. Let's replay it here. The flame splashes out ahead of the ignition interface there, and it splashes the flames out into the new fuels, providing intermittent heating, convective heating of all these particles that are sitting out there. And so in the past, most people would say, well, there's radiation coming off from the fire, and it's heating up the fuel particles, and they're slowly rising up to ignition temperature. But in fact, what we're seeing, and I'll show you a few slides from here, the particles are largely unaffected as far as ignition goes by the radiation, and they wait to be bathed by flame, because what happens when they're bathed by flame, they can't cool off then, right? They're sitting, instead of in cold air, they're sitting in very hot air. And so if they're convective cooling, if they're cooling by convection very efficiently, then they're also heating by convection very efficiently. We've measured these bursting patterns, these frequencies, with arrays of very fine wire thermocouples. We usually use 64 thermocouples in our burn so that we can see the coherent motions of these bursts and see how far out they go ahead of the flame zone. And so this is a kind of a schematic here on the left-hand side showing, looking down at the flames. And if you had a series of thermocouples in there, they extend here off to the right-hand side where you're seeing a temperature trace from each one. And so the very bottom one in black, the bottom temperature trace in black, shows a very spiky behavior of the temperature as the flame zone approaches these particles, right? Because the forward bursting is highly intermittent. And if you look carefully, you can follow one of these bursts as it traverses all the rest of the thermocouples. You can see the coherency in the motion of these flames as it moves forward. So it's not just random darting and random turbulence in the flames. There's actually some really organized flow to all of it, organized and quite predictable in the average sense. So what we're seeing here in the intermittent region as the flame front approaches, you're seeing highly intermittent bathing of the fuel particles ahead of the arrival of the flame zone in the ignition. And what's interesting about this whole process is that it scales. In a lot of the buoyancy studies that people do, like pool fires, they perform a scaling of dimensionless groups, and in this case, the frequency on the left, on the y-axis here, has been encoded into a number called the Trough number. It just takes out the dimensions of length and time in it, and then the Freud number is a ratio of wind speed to some length scale, in this case flame length. And so when we plot the variables from our experiments out on this graph, you see a very nice straight line on log-log scales. And we can also plot the frequencies and associated with flames from crown fires, from our stationary crib burn, and from our grass fire experiments on the same graph. And what it suggests to us at this point, and we're doing a lot more field testing of it as well, is that the behaviors we're seeing in the laboratory scale all the way up to the biggest flames that you can see in the field. And we are limited here. We don't have a lot of points from all the fires, and not all fires could be used to test this idea. We have to have the right configuration in order to really test it. But this is very encouraging, and if it didn't occur, we would be quite disappointed, because it should occur. If the temperature of the flames is the same in the lab as it is in the field, then we should see some kind of buoyancy related scaling, whether it's this or something else. So that's kind of what we're looking at. To finish the story with respect to particle heating and heat transfer here, if you instrument one of the particles, put some thermocouples on the particle, and then right next to the particle, very fine wire thermocouples, and as the flame front approaches, you can see how the particle is heating. Let me explain here. On the left-hand side is kind of a full time history. The red line is the radiation received by the particle, and you can see it goes up to close to 30 kilowatts per square meter. So that's at the peak. The blue line there is the air temperature, and that would include the flame temperature when it's present, so just the gas temperature next to the particle. And then the black line is a thermocouple right on the surface of the fuel particle, and so that's the black line. So on the right-hand side, you can see it blows up to the last 20 seconds of this particle's life before ignition. And the main thing to point out is that what the black line is doing as it increases in temperature is that when it encounters one of those blue spikes, that's one of these flame bursts coming ahead, the particle temperature rises very quickly, and then it slowly cools off in between bursts, and then it hits by another burst right here at 126 right there, and then it cools off a little bit, and then it keeps getting hit by these bursts, and eventually stair steps its way on up to ignition. So the fuel particles are responding to this intermittent heating and cooling that's experienced out in front of the fire. Even as the radiation goes up, the particle can still cool off. right? In between these flame bursts, what you're seeing is a cooling of the particle, despite the fact that there's increasing radiation. So this kind of just proves the point that these fuel particles are not very sensitive as far as ignition goes to the radiant heating, that is pretty much dependent on the presence of flame or cold air and in some intermittent pattern that allows them to heat. So that's a story on heat transfer ignition. Let's talk about live fuels a little bit. Live fuels are totally different than dead fuels in many, many different ways. Not all live fuels will ignite and burn. Some readily ignite and burn. This is a grand fir branch that has been subjected to a stream of flame temperature air. It's just electrically heated air, just like a hair dryer. It's just that it heats it up to flame temperature. And so the advantage of having a heat source, a pure convective heat source like that, is that you can see what's going on the particle versus if you bathe it in a flame. So most people who study convection, what they do is they just have a flame source. But if you really want to see what's going on the particle, you need to get rid of all the flame, and you just have the hot convective gases, hot air. So on the right-hand side is a thermal video, and you can see all of this bursting, right? When the grand fir branch is introduced into this hot air stream, the very rapid heating takes place, and the cell contents heat up very rapidly. They boil, it's under pressure, and then they burst, shooting out the cell contents into the flame or into the hot air stream. And so there's no flame in any of this except which is produced by the branch as it starts to ignite. And so the point of this is not to tell you a conclusion here, really. It's just to show you some of the complexities of trying to understand live fuel ignition and burning, because it's totally different than just dead needles or dead grass, dead branches, dead wood. It is not that. And there's so many differences with respect to different species. I'm not sure really what the future is for us understanding this. I think we really need some breakthroughs in live fuel ignition and burning before we're going to start to put some order to all this chaos. It's just important to realize that it's not well understood at this point. Let's have a look at the other part of this equation, and I'll take some questions. That is burning rates. And so the main questions we're trying to ask here is, how long do fuels burn? What is the rate of energy release and heat release for fuels burning in some arbitrary configuration? If we really understood this, you would say, well, we could take an arbitrary assemblage of woody material, right? Some fine material and some dead sticks, and we could pack it or pile it up in some way, and we would be able to, once we knew the properties of that pile, we would be able to predict how long it would burn. And someday we would hope to get there. We are not there yet. We still can't tell you how long it will take to burn any arbitrary configuration of fuels. And until we're able to do that, our models are just not going to get any better. So one thing we do here is we study this independently. Right? This just reminds you that these are discrete particles, right? We're not just dealing with a big block of wood. We're dealing with multiple packing and size distributions and everything of material. And here's a crib. Cribs are used, I've already talked about them a little bit. They're different densities and sizes of material, all sorts of things. And we use cribs a lot because they're well ordered and well characterized. And if we can't understand how these stupid things burn, we're never going to understand how fuels out in the wildlands burn. Okay. And so here's what's known. We know that as you change the packing or the porosity in fuels, you change the burning rate. If you can compact them really pretty densely and they don't burn as fast. This isn't really very novel. This little graph here shows don't worry about the numbers on here, but the x-axis is a porosity factor. Densely packed fuels on the left-hand side of that line, they burn at a slower burning rate than the ones that are loosely packed. So there's kind of a curve there. This has been pretty well known for many decades. And moisture content certainly affects this. The particle sizes certainly affect this. We already know this. That's not the problem. The problem is, how does it work in wind, for example? All these crib burns that I showed you here, well, this graph here, this is all done in the absence of wind. But as we know in wildlands, wind is an important factor, whether it's wind forced onto the fire through ambient conditions or whether it is induced by the fire itself. Wind is part of the combustion environment. And so these experiments show us that we have no idea how this is working. We have wind speed on the x-axis, and some of these cribs in different configuration increase in burning rate when they're introduced into a flow, and some decrease. So I wish it wasn't that. It's certainly an unexpected thing, and we're still doing more work on that to try to understand why some fuels would decrease their burning rate when they're introduced into wind. It has to do with particle sizes and packing, all the other factors. So this isn't just a straightforward thing of just saying, well, every time you put fuels in a wind and blow on it, they increase in burning rate. That's not true. So it's more complicated than that. But there's even more profound questions, I think, when it comes to burning rate. And we're just kind of scratching the surface on this at this point. But the question that we face is right at the top there. Are big fires different than larger small fires? Right? When a fire gets to be a certain size and a certain character, is the burning rate that goes on there different than simply what goes on in a small fire? If you look at all of our models right now, not just the operational ones, but even the research models, the answer is no. They're exactly the same. Big fires and small fires, right? And so we have the same equations and everything else for little ones as well as big ones. But here's the thing. It's been suspected for quite a long time that big fires actually do exhibit quite different burning rates. And it has to do with the fact that when you increase the area of a fire, the cold air can't get into the middle of it. And therefore, the temperatures of the air above the fire, I'm not even talking about the flames, I'm talking about the temperatures of the air above the fire are higher. It's a higher center line temperature in the plume. That means there's a lower density, a lower hydrostatic pressure in the middle of it, which induces a very strong inflow. And as the very strong airflow past these fuels, certain kinds of long burning fuels, you can change the burning rates a lot. Just ask any Boy Scout or Girl Scout that to get a fire going, you blow on the coals, right? And that increases the temperature of the glowing combustion and increases the burning rate. Well, none of our models are as smart as Boy Scouts or Girl Scouts, I'll tell you that. So have a look at this set of videos here. I'll replay it again. The one on the left is a crib just burning. This is accelerated 8 times the natural speed so that it goes by quickly. But the crib on the left is burning just out in the open. The crib on the right, let's play this again. The crib on the right is stuck underneath a chimney that serves as kind of a small scale model of a large plume. And you're seeing a running strip chart kind of at the bottom where you're seeing the mass loss rate of the fuels. The orange collection of dots there, the orange trace, that's in the chimney, and the blue line there is without any chimney, just in the open air. So I'll play it one more time and you can watch how fast, what difference it makes. The same exact crib, same moisture content, everything is the same except we have a chimney above it that changes the hydrostatic pressure and then the airflow into the crib, the ventilation of it. So where this becomes relevant is in long burning fuels like large pieces of woody material or duff and litter. You can change that from glowing combustion or smoldering combustion into flaming. As you ventilate that, you ventilate those fuels, they can burn at a higher rate. And so the burning rate of the fuels very likely is a function of the influences of the fire itself. And this is not modeled anywhere. We don't have any model here that is ready for any kind of use. It's simply documenting what's going on and trying to figure this out. But it means that someday, hopefully, we will be able to put in proper energy release rates for very large fires. So that's my talk on a number of aspects of processes going on at fine scale. I'll be glad to answer any questions.
Excellent. Thanks, Mark. We do have a question from Jay Charney. Jay, I'm going to try and unmute you and see if you can, you should be unmuted. Did you want to present your question, or did you want me to read the one that you sent in?
Yeah, I'll go ahead and present it. No, I'll go ahead and say it, and I'll try not to say it in too many words. Okay, so Mark, I don't know if you can see the question in the chat window, because I know you're presenting. It's complicated to read while presenting. But first, I wanted to thank you for the interesting discussion. That was some neat things, and I've seen some of that before, but some of that was new to me. My question is one of scale. Thinking of this as a meteorologist who's kind of working from. I'm a researcher working on developing tools for the forecast question, and forecast meteorological information is, I think one could argue, at best available on scales of a few hundred meters as far as wind and temperature and meteorological variable information, and perhaps even coarser than that. Are we ready to even start talking about trying to span the scales between what's available from a meteorological forecast perspective and the sorts of processes that you're talking about in this presentation, so that we can work towards either using existing tools or developing new and refining additional tools for providing fire managers with information about how meteorological processes might or might not affect these sorts of processes you're talking about here. So I know it's a mouthful, but that's kind of what I was aiming towards.
No, that's a great question, and that is the question, right? I think you already know the answer to this, really, that we're not going to be able to brute force any computations from fine scale processes like what I'm talking about here, or finer, all the way up to the scale of the meteorological scales, or for the biggest fires. We're not going to brute force that computationally, and so I think the way that we're going to be able to bridge that gap in scales is through some clever modeling, parameterizing fine scale processes so that they still adhere to the physical principles, but parameterizing them such that they apply at the larger scale. And since we haven't done it, I don't know what that is. It's not like I have a plan for how that works, but in the past, on the fire spread part, we just haven't understood how fires are spreading at these fine scales. My vision is that at some point, these will work, this information and other stuff will work its way into numerical models in one way, and in others come up, it'll be represented in even other models, simpler models that then would be able to scale to this meteorological scale. Not sure if that's a very satisfactory answer, but.
Well, I'm a scientist. Everything's a satisfactory answer, but yeah, I understand what you're saying, that there's a lot of uncertainty, and just spanning the scales is a complex problem no matter what we're talking about. And one of the points, I guess, that I often talk about when thinking of how to span these scales is whether we can sort of separate our thinking, to a certain extent anyway, into scales that are almost completely dominated by the fire processes themselves, so by the heat and the release of energy from the fire. And how far away from the fire do you have to get before the background wind matters at all? Let's say, just to pick an example. I mean, is it 1 meter? Is it 5 meters? Is it 10 meters? And how does that relationship vary based on fire intensity? And based on that sort of determination, you can start to ask questions about, okay, when do my meteorological variables matter? And at what scales are we going to start getting answers that have any real meaning for what's going to happen on the fire line? And so I think that's another way of saying roughly what you just said, is that there's ways of simplifying elements of it and trying to find the connections that matter for what we're trying to predict, I guess.
Yeah, and one other aspect of this is, when can we use simple models that don't assume very strong coupling with atmospheric kinds of variables? When must we consider those coupled processes in order to have any hope of understanding what's going to happen out there? And we don't know that. We don't know where that dividing line is.
Mm-hmm. Yep. So, all right. Well, again, thanks very much. It was an interesting presentation.
You're welcome.
Thank you, Jay. Any other questions? Okay, with that, Mark, I would like to thank you very much for presenting to us today. We enjoyed your presentation, and as always, we have recorded this presentation, so people that were not able to see it today, spread the word. If they are interested in this subject, they can look it up on the National Weather Service Fire Weather YouTube page. Again, thanks, Mark, for presenting, and with that, we will be back on another Fire on the Fives with more fire environment information. Thank you.
Cool. Okay, bye-bye.